Hello class and welcome to today's lesson 2.3. Today we're going to talk about biconditionals and what those are. So today's goal is that you'll be able to write biconditionals and recognize a good definition. So again, like all other videos, make sure if you need to pause it whenever you need to, catch up with the work, and then move forward. So looking at our first one here, if today is Saturday, then yesterday was Friday. Is the converse true? So we have to use our prior knowledge here. Right? Our converse is if Q, then P. If Q, then P. So right, our statement here is written as a conditional as if P, then Q. So let's change this around. So is the converse true? We have if yesterday was Friday, then now P, today is Saturday. So if yesterday was Friday, then today is Saturday. Is that a true statement? Well, let's think about that. If yesterday was Friday, right, the only day where yesterday was Friday would be Saturday, then today is Saturday. Yes, that is a true statement. So what we're talking about today are statements that are both true as a conditional and true as a converse. And how we do that is we write this biconditional. We use the phrase if and only if. Right? If it is true both as a conditional statement and a converse, we can write it as today is Saturday if and only if yesterday was Friday. Right? Because it is true both ways. If and only if. And so a biconditional is a single true statement that combines a true conditional and its true converse. So if the conditional and the converse are true, we can then make a biconditional. So we look here, biconditionals are true if the conditional statement and the converse are both true. Right? They have to be true reading them forward and backwards. Right, forward and backwards, converse or conditional statement. So now talking about a definition. Right, when we look at something, what makes a good definition? There are three parts to it. First part is it uses clearly understood terms, commonly understood terms, or already defined language. So they're using things that we know already. We don't have to look up terms or things like that. Two, they are, precise. They avoid words such as large, sort of, or almost, ones that don't quite give us the best definition there. And then the third thing is they are reversible. They can be written as a true biconditional, or they can be written as an if and only if statement. Again, feel free to pause if you need to. I'm going to move forward here. So, is this statement reversible? If so, write it as a true biconditional statement. So we're looking at this statement here. It says an angle bisector is a ray that divides an angle into two congruent parts. So we think about this, is it reversible? Is it true if we were to say an angle divides an angle, or a ray divides an angle into two congruent parts, then it is an angle bisector. Right? Both of those statements, either way we read it, is true. So we can rewrite this statement as an angle bisector a ray, sorry about that. So a ray is an angle bisector. A ray is an angle bisector if and only if it divides an angle into two congruent parts. Right, so we have that statement now as a biconditional. A ray is an angle bisector if and only if it divides an angle into two congruent, sorry that C looks like an R, into two congruent parts. So now we look, is this a good definition? Right, is reversible? Yes. Clear, concise language? Yes. And it's precise, it gets at what we need to, and it's words that we know. So yes, that would be a good definition. Right, a ray is an angle bisector if and only if it divides an angle into two congruent parts. Now we have this one. Linear pairs are two angles that share a side. So we have to think of this both ways. So first, is it true if an angle or if two angles are a linear pair, then they share a side? Right? We think of that way first. So if two angles, I'm going to shorten this up really quick, are a linear pair, then share a side. Right? If we look at that statement, if two angles are a linear pair, then they share a side, this statement would be true. Now we look at the converse of that. If two angles share a side, then they are a linear pair. We look at this statement. Is that true? And right, if we look at this statement, this in fact is not true. Right? Because you could have two angles like this. I'll give an example. Right? This is a counter example. Notice I have angle ABC. It shares a side with angle CBD, but together they are not a linear pair. Together they are not a pair of angles that make a line. So that'd be no good. So the statement is true, right? It's converse. If the converse is also true, combine the statements. So we look here. If x is equal to 5, then absolute value of x is equal to 5. So now let's write the converse. So this statement, first we check that statement is true. Now we go, if absolute value of x is equal to 5, then x must equal 5. All right, we got to think to ourselves, is there a counterexample? Is there something that could make this false? And yes, the answer is x equals -5. If you plug in x equals -5 to the absolute value, you do get 5, but right, x does not equal 5. Now we check this one down below. We're going to rewrite this as if 3x plus 2 equals 14, then x equals 4. So we check to see if these statements are true. So if x equals 4, then 3 times 4 plus 2 has to equal 14. That is true. And now we go the opposite way, right? If 3x plus 2 equals 14, then x equals 4. Well, right, the only thing to make this a true statement is if we plug in the number 4. Right? If we plug in the number 4, that is the only way this is true. So this is a true statement. So now we're going to rewrite this as a biconditional. So 3x plus 2 is equal to 14 if and only if x is equal to 4.